Buonasera a tutti, grazie per partecipare a questo incontro, a questo nostro seminario. Bene, ho il piacere di presentare il professore Baskonus, professore ordinario della facoltà di matematica e applicazioni presso l'Università di Aran, nella città appunto di Sallur. Bene, il professore è autore di 200 articoli scientifici anche molto importante, noto a livello internazionale. Lui principalmente, il professore appunto Baskonus, si interessa di modelli matematici applicati alla biologia e anche appunto alla radiologia, con lo studio e la determinazione di soluzioni di equazioni differenziali, lineari e non lineari, parziali e anche frazionali. L'argomento chiaramente che il professore Baskonus oggi ci parlerà sarà
Professor, thank you very much for inviting me, and in such a kind, excellent university and the platform. It is really, I do it. Yes, it is really important stage for me as well. I can.
Yes, you can.
Okay. Okay, I think it is better now. Okay. It is a huge honor for me to be here, and it is a really big pleasure for me, especially this is the second one for me. And I would like to extend my sincere thanks and the Professor Ciancio and the department and the Professor Armando. And I would like to start with my talk title, especially newly developed techniques to the biological models. With the starting slides, I would like to start with motivation. Why such a kind of model is very important. From all over the world, many humans and kind come across and witnessed real-world problems, especially health problems. And in the world history, we can see some problems in malaria, and Spanish flu is really important in the community from all over the world, especially the world population, and almost 50 million people affected by such a kind of flu. And the measles is also very important. Another one, real-world problem, biological problem, that also is the same. And newly now we are living in the coronaviruses. This is also really important from all over the world and for all peoples. And shortly we can see it's 40 kind of classification. And this is presented by International Committee of Taxonomy of the coronaviruses. It has mainly 4 different classifications, but subsections, at least till now, more than 40 classification of the coronaviruses. And we can see their viruses, species, different human, pig, birds, wilds, and many others we can see also. Mouse, rat, pig, like this. So, in a basic stage, we can see in here, in a brief manner, and briefly, this is the general structure of how coronavirus spread. There are a lot of coefficients and parameters affected by different situations according to their living style, lifestyle. But here, briefly, we can see its main structures. Into here, some parameters, when we ignore, we can see it is a simple and a basic form in the ordinary differential equation systems. This mathematical model constructed by using data from China, especially Wuhan area, especially in the W in here means is Wuhan. It's changing according to the place, relation to relation, city to city, it is changing. Of course, we can add and exclude and eliminate some terms and some coefficients. Now, secondly, in physics and chemistry, till now, nuclear weapons is really important in human life, especially from all over the world. And now there are several evidence, Iran, Syria like this. North Korea also 2013. And in biological and bioterrorism, this is really important, especially microorganism based in this sense. And we can extend its importance in the mechanical and the biological engineering area. And we can continue like this. Chemical weapons, like blah, 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 we can extend this one. And smallpox also we can give such a kind, 15th century also. So we can extend such models. As an example, we can give, this is a population model, tuberculosis, HIV, and AIDS, combination of them. And such model is only spreading time, according to time, ordinary differential equation has been used into the here and the non-linear. And who is also studying and following actively progress. What kind of development and progress can be introduced and produced to the literature? So like this, another one, and also historical evidence of tsunami. It is a really important one. By using mathematical models, we can estimate when they will occur, how we can convert this giant problem to the useful energy. We can convert this one by getting and by considering in a suitable steps beforehand. So we can extend such kind of problems for motivation sections. All these mathematical, all this area can be used by using mathematical facts, especially nonlinear, ordinary, and partial differential equations. We can use this one. And we can observe their deeper properties of investigations, such kind of model. These results will present us better and deeper properties, different kind of senses, maybe hyperbolic, gravitational energy, like this. So, especially in this talk, I would like to shortly and briefly submit general properties of these methods. What will we do in here? What is their open problem? And what can we do as a future works? And there are such kind of empty and open problem to the study on it. So, briefly, we can see homotype analysis techniques. It's divided by different kind of partial differential equations, linear and non-linear, especially fractional one into the here. And we can apply by Laplace transform into the here and inverse Laplace by using homotopy. You can see. So, in here, as a Taylor series extension, because such kind of model method is based on the Taylor series solutions form. And now we can see its inverse Laplace transform from the coefficients, and we can apply homotopy polynomials, given by such kind of definitions. After that, we can write its series solutions form given by 21. Now, as an application in here, 2020 coronavirus outbreak, when outbreak in Wuhan area, and we observe such a kind of mathematical model for Wuhan area. In this model is a basic one for the first outbreaking times, in those times. And so In here, S means symbolized to susceptible people, I infectious people, R reported symptomatical peoples like this, U means unreported symptomatical peoples. So, briefly, we can write such a kind of model for transfer and the spreading of coronaviruses. This mathematical model formed by using data reported by China, especially Wuhan area. So, in here, we can use it is initial condition by given by 2023, and we can take its Laplace transform 24, and by getting non-linear operators, especially from the homotopy terms, we can find such an iteration equations. So, in here, if we apply necessary values of the parameters and reported by China, and we can write this recurrence form, and its first step iteration formula given by 2090, and in here we can see it's a parametrical simulation and a different kind of the parameter simulation. In here, what is the effect of fractional operator in here? We can see, and the blue one is alpha is 1, and the others alpha is 0.9, 0.8, 0.7, and 6. This means that, especially in the first 100 days, for example, we can see it from here, and it's in the first 100 days, it's spreading almost 1,000 and 100,000 people. This is really very important. And so, we can also say about our model in the right side for U, also very quickly spreading and presenting, and such people's numbers will be quickly high. So, this comes from the parameter, fractional order parameters, and our values of the parameters repeated by Wuhan area in China. So, and secondly, iteration techniques given by 1999, and here variation iteration techniques, and also we can use this one for our models, because these models based on the real data. In this case, how our techniques affected and affect such kind of models, and what can we say? So, in here, this is the recurrence form, iteration formula for the test function of the solution, and this is the limit values, because it is also based on the series solutions, and so this is our model, can be based on the transmissibility of the coronaviruses, and especially in those times, these mathematical models produced by using several areas of China, and in here, W means also Wuhan area. If we take W as 0, this goes outside of Wuhan area. So, if we investigate such physical problem in Italy, for example, in the Messina, we can add here such a kind of dependent variable. And after that, we can investigate it is different situation, the weather condition and the other situation we can add and exclude like this. So, and these are initial conditions by using different parameter values. These parameter values should be very consistency and should be official one, especially reported by official way. But in this stage, we have to be more and more careful, because some cases, some cases should not didn't report it in the official way. This is a problem for mathematical, and it should be solved also. So in here we can see what is the definition of the parameters and the physical meanings. What is their physical meanings? We can see, and in here, for 6 different parameters, iteration formula can be given like this one, and lambda in here especially given as -1. If you put it together, you can obtain such an iteration formula. These are the first steps for the parameters of system, and we can obtain such kind of shortly written in here.
In the linear.
Yes, this is the second.
In the linear. Yeah.
No. This is the first steps of the solution. Our solution is confirmed by.
Yes, but linear to.
No, not that. This is the first one. The second one we can see in here, and these are the explanation of the parameters. And this is the second one. And now we are using the first one. If we found here, it will be non-linear. We can see now. In here, we can see now. In the second one, it is the non-linear, and the third degree. This means that in the second term of the solution formula, we obtain third degree. If we find the next one, third one, for example, W3, it will go to 4 or 5. This is high nonlinearity. It is very important for the physical meanings of the problem. Now we can see its surfaces. It is red one, and U very quickly goes to logarithmic function, exponential function, exponentially growing. Now, this means that how we can say something about this one. In the 12th day, we can see any people in the 12th day in here, any people bring coronaviruses, at least 200 people within the 2 weeks. This means that how coronavirus can be spread via any people, normal people from the society. So these are the parameters, values of the parameters shortly written in here, and these are separately power of the parameter in the system, and like in here also. Yes, we present some discussion and remarks in here. We can say that each class of the system also simulated estimated behaviors. This is important. Our simulations produce for some important information, some future behaviors of coronaviruses. For example, this model given by the first data. What is the next situation? What is the next behavior of coronaviruses? In here, we can see that by using these graphical surfaces, we can see that coronaviruses will be spread quickly. Let's go outside. In reality, we can see that exactly in the world, from all over the world, coronaviruses quickly spread. This is evidence of the theoretical data. And also, this giving us the real form of mathematical models. So, next one is Bernoulli's application function method. Such method is also used to obtain analytical solution. The first two techniques giving us numerical results, approximate results, but these two methods giving us exact solution for the partial differential equation. Till now, our models were ordinary differential, but in here, if we add local place, for example, Messina as an x, in this case, it will be partial differential equation because we are working on the determined area. In this case, we have to apply partial differential. We have to symbolize by using partial differential equation. In this case, how we can solve this one? In here, we can see such a kind of partial differential equation, and we can convert it ordinary differential equation. Now, here is firstly submit to the literature 2.4. 2.4 is a newly developed version of this method. And if U in here, 2.4, is a solution, test function of the solution formula of given by 2.3, in this case, we need U prime, U prime prime, U third prime. In this case, we have to take its derivation. This is the rational function derivation. In this case, F prime is Bernoulli differential. In this case, it's named as Bernoulli. It is a sub-function, sub-equation function method. So, it's a newly formed divided by the same series solution, and G from 0 summation G from 0 to the M, and we can write this one. So, when we apply this technique to the mathematical model, yes, if we solve in here 2.5 Bernoulli differential equation, F also know it like this, 2.8 and 2.9. So, as an application, to solve such a kind of mathematical model, Kundo-Echo's equation, is really takes so much time. And now, when we apply our newly developed technique to the here Kundo-Echo's equation, firstly we have to convert this one, ordinary differential equation, by using 2.11. This is the wave transformation formula because it is independent variables x and t, and eta means combination of them. After that, if we put our model equation 10, we can obtain here, and if we take W is equal to the minus 2 alpha, our model is in here is a complex model. Complex side, imaginary side of the model goes to 0. In this case, we have only one real part of our model. This is the does not contain any complex term. Complex term goes to 0 under this condition. So, by using balance presso higher degree and higher order, we can find this relationship between of them, small m, and capital M. And here is newly formed. What is newly formed is small n. Small n comes from our general properties of the small n here. We can see here small m, small m. Now, in this case, how we can use this small m? This is infinity. If we take the smallest values of parameter in here, capital M, small m, we can find many coefficients. These coefficients produce to us new solution, analytical exact solution. So, K is 1, we can see is minimum values of m. We can take like this one. In this, our solution is this, 2.14, and if we take its necessary derivation, and if we put here 2.12, I need U prime. In this case, this is the U prime. I will put all these parameters to the non-ordinary differential equation. Then I can obtain a system of F, capital F. All is 0. How is it possible? All coefficients should be 0. In this case, I can obtain a system. I have to solve the system by using packet program, maybe Maple, MATLAB, Mathematica like this. And after that, we can find the coefficients A0, A1, A2, B0, B1. In our algorithms, we found 300 different values of these parameters. We select some of them in a suitable way, and satisfying the strain condition is also in here. And after that, we obtain its results. This solution we checked by using the main, putting into the main model, satisfy or not. After that, we plot its surfaces, and we have to check it satisfy or it is simulation figures should be the same in real data, in real world problems. Is it the same or not? So we can see in here some of them, the coefficients. After then we can find such kind of solution, 2.18. Yes, it is the surfaces this one. The surfaces is valid for x smaller 0, because right in the right side is not traveling. This comes from coefficient. Now, two-dimensional surfaces, we can see it's also going in here, come the H's equation, ionic symbolizing and ionic behavior into the air, not sharply cut down. It's going to the middle. So this is the next coefficient, the next solution. Yes, in here we can see it's more deeper surfaces. Also in here we can see x is 0, but in the right side it's continued, not chopped down. Yes, in two-dimensional surfaces we can see. These comes from coefficients, the values of the coefficients. The next coefficients given us such a kind of solution. All these solutions satisfy the model. We have checked. Yes, in the right side. In this case, in the right side, we can see it's comes from suitably, then sharply going, and this is a harmonic solution in the right side. We can see now in here, it comes from like that, this side, after then sharply down and close. This is really important. So, the last method, Sine-Gordon expansion function method. This method is also an analytical method and a very powerful one. And recently, for the last 5 years, we developed and extended its different types. Yes, solitary wave solutions. And because it is really very, very, very powerful, and we can obtain more deeper complex hyperbolic trigonometric function, because such kind of solutions is important. Oscillation in a model, and for example, in the vessel, how fluid behaviors, how can we see it? Then we can obtain its surfaces. So it's based on the Sine-Gordon equation. Basically, in a basic sense, we can obtain two different solutions, two different properties given by 8.6 and 8.7. These are important. Why? We will use sine and cosine to calculate parameters, values of parameters. After that, we will use second hyperbolic and tangent hyperbolic. Because our independent variable is Haci in here, and in our properties, we can see from here, independent variable is W. We are using these properties. So, as an application, as an assumption of the test function solution formula given by U Haci, UW, tangent hyperbolic. Tangent hyperbolic was sine W, and the second hyperbolic was sine W. After that, this is our test function of the solution formula. We can use these two important properties. After that, we can write here 8.10. Now, as an application, in here, ion sound wave equation to solve such a kind of problem really getting too much time, effort, and computational power, and like this. So, how we can solve this one? And such kind of problems, the real world problems, especially arising in the mathematical biology. Now, if we apply our wave transformation formula into the here, traveling wave transformation, we can obtain 8.14 short.
The phase, I think it is parabolic.
Sure, it will come. We will see the results. Sure, we will see into the results.
Okay.
Now, in here we can see its ordinary differential equation in this form, and u prime prime u power 3. Now, by using balance principles, higher degree and higher order, we can see n equal to the 1 because we need to read. So, if you put n equal to the 1 into the 8.10, we can find this one. But we need u prime prime into the here. This is u. This is u. We need to u and u prime prime. How we can calculate this? Sine. What is the derivation of sine? Sine derivation is cosine. But w prime, what was w prime? W prime comes from the general properties of from here. W prime, sine w. This comes from general properties of the method. So, in here, let's see, sine derivation is cosine. W prime, sine w. Maybe some mixing, but we are using the general purpose of the method. So, some people may ask how sine derivation is cosine w and sine w. This comes from general properties of the method because w prime equal to the sine w. In the same manner, we find u prime prime like this. In here, cosine, for example, cosine derivation, sine. W prime, also sine square. Into the here like this. This is the first and second. If you put here u and u prime prime into our non-ordinary differential equation, and we can obtain here, all is equal to 0. How is it possible? All coefficients should be equal to 0. In this case, we can obtain a system like this. We have to solve the system by using different parameters, different packet program. Now, what is the main advantage of sine expansion function method? This is the, now, in here, sine square, we can use trigonometric properties. What was the sine square? Sine square is equal to the 1 minus cosine square. In this case, this term goes to the cosine square, then constant term. In this case, our system is changing. Then we can find another form. This is the power of trigonometric properties for our method. Now, if we solve this system, we can find such a kind coefficient, and there are 5 different coefficients from here. By using these coefficients, we can obtain different solution formula. All solution formula satisfy our main model. And you can see in here, exponential. Tangent hyperbolic is also exponential. This comes from main properties of the ion atoms. Yes, now we can see it's 3-dimensional physics and 2-dimensional physics. It's completely traveling. And now the second one, you can see traveling, imaginary part, real part. It's absolute values. And the next, this one is also the same. We can see. And the fourth one, we can see more deeper ionic behaviors. In here, this solution is used to expression gravitational energy. Gravitational energy. How we can calculate gravitational energy? Exponential function, then tangent hyperbolic function. In this case, gravitational energy is affecting ionic wave behaviors. Ions were affected by gravitational energy. This is important. In our mobile phone, PC, laptop, we are using many such kind of ionic values. This is very important. This is only one solution. We have found many solutions. And here we can see its ionic wave behaviors. And also we can see from here. This is also absolute value is also prevalent. Next one is also we can see here. And this is also can be used for symbolizing gravitational potential energy. Yes, more complexity we can see in here, and also from them. Okay, in here, by using as a discussion and remarks, we can extend its coefficients and the values of the coefficients. We can select more different values of the parameters, and we can, yes.
Catani dice che non riesce a collegarsi.
Anche con quando...
Ok.
Hai visto il cameriere?
Ok.
Non riesce a non riesce.
Okay, into here, our results used to symbolizing gravitational energy. So, in bigger than era, we can see ionic behaviors here, also like this one.
Quello di Minervo.
Sì, se lui clicca sul link che c'era nell'email, può entrare come guest.
Può entrare adesso?
Certo.
Sì.
Puoi entrare adesso, mi dicono adesso, puoi entrare?
Sto dentro, ma c'è una sola persona, c'è un certo aspetta. Prima ce n'erano tre.
Quindi da 5, quindi da 5.
Adesso io esco e provo a rientrare.
Ah, ma lei vede 2 riunioni avviate?
No, questo qua sto parlando del telefono. Ce n'è una sola.
Poi torno a partecipare.
E vedi se c'è la fare.
Prima c'erano altre 3 persone, adesso c'è un Giuseppe Haci che è in attesa, non lo so chi è.
Giuseppe Haci, non lo so.
Perché si è collegato ad un'altra riunione.
Ad un'altra riunione ti sei collegato.
Quindi abbiamo 2 adesso.
E questo è il link che mi avete mandato.
Questo qua mi hanno dato, per colpa mia. E qual è adesso?
Dove c'è scritto la data 19?
Dove c'è scritto la data 19?
Dove c'è scritto 19 luglio 2022. Ce n'è una del 19 luglio 2022 ore 16. L'hai trovato?
Perché qualcuno ha avviato un'altra riunione.
Quello che mi avete mandato è questo qua, che cominciava alle 16.
Siamo noi, 19 luglio 2022. Quindi si sono...
Non ho capito, ma sono entrato qui, c'è sto Giuseppe Haci che è un'altra riunione.
Ma cos'è? Ok, sì. Va bene. Scusa, che c'è stato... Aspetta.
Vabbè, adesso esco da quella riunione là, va.
Vediamo. Ok, me ne sei rientro. Grazie Carluccio. Ciao.
Vedi se me la puoi rimandare.
E come ce l'abbiamo da mandare?
Va.
Aspetta, vediamo se te la riesco a rimandare.
Non ho detto. Non trovo la faccia.
Penso l'abbiamo fuori. Non funziona.
Ma stai a nome?
Ci sono... Così.
Abbiamo il suo indirizzo email?
Sì, aspetta, glielo dico subito, aspetta. Catani quando è? Com'è? No, le mail, aspetta. Come il... Mannaggia, non ci posso. Ecco qua. Catani. Cattani @unitus.it. E chi è questo? Pronto? Risposto?
Perché c'è Outlook che ha i suoi...
Ti hanno chiamato forse, vediamo se...
No, ancora no.
Ah no, aspetta che ti stanno mandando il primo. Ci sono due conferenze, capisci, contemporanee. Non lo so io. No. Ma non è nei nostri argomenti nostri, no. Il titolo della conferenza qual era? E questo è, e ce n'erano altri. E questo è quello là. È giusto, perché erano le cose, modelli matematici.
Può controllare se ha ricevuto il...
Vedi adesso.
Nell'email.
Ah?
Nell'email.
Nelle mail, forse c'è da dare. Ci trovi ora? Ah, ok. Page 83. Ok. Guarda. E forse il permesso. Le date il dato del permesso. Ok.
A me risulta...
Allora risulta. Ok.
A me risulta
bene. Allora, Mehmet, continua il CIS.
Okay.
Poi ci sentiamo dopo.
Okay.
Mi ascolti? Sì.
Thank you. As a discussion and remarks and open problem in here, as future work, we can develop this technique also divided by in a rational form, in logarithmic form, and trigonometric function form, and we can select more deeper different values of the parameters in the system, and as a physical means and in the biological era, these solutions can be used to, how can be affected by gravitational energy, and this is also important. We can report and extract such kind of results. Yes, we can see in here the simulation, the big area, and it's commonly and intensively behaviors of ionic wave distribution from here, and also from, we can see these are very intensive ionic behaviors. Yes, now we can see more area. Okay, conclusions. We can report in this talk the results and to apply a new method to the mathematical models. And we can apply this method also biological models. And we can see and investigate its distribution in the frame of wave aspect. And we can compare its surfaces to three and the contour surfaces. How we can observe in the future this problem. For example, coronavirus, how it will be spread. We can see, and the strain condition also we can report it, and the contour surface also plotted, and the accuracy of the method can be compared by using real data and theoretical data. Yes, these are some useful references we have used in here, especially Western Encyclopedia. This is also physical and biological meanings of hyperbolic trigonometric function, hyperbolic waves, wave distribution, and it is also really important. And the David Morin books, chapter 5, it is also we are used in here, and Kundra-Echo's equations from here, Watagala and other polynomial function. And thank you so much.
Because it is possible to show that the mathematical, in particular theoretic part means the study of the experimental.
Exactly, sure, exactly. We can.
Thank you so much.
C'è Carlo, Carlo risponde.
Qualche domanda da casa? Da casa qualcuno vuole
Carlo, l'hai sentito?
Professor Carlo.
Yes, thanks a lot. Unfortunately, I came only at the end because some problem with connection.
No
Can I ask something?
Sure.
Okay.
Carlo, la registrazione te la mando, va bene?
Va bene. Okay, grazie. Now, the question is the following. There are many different types of solitons, especially you were studying dark solitons.
Yes.
How they could be related to some, what kind of biological meaning can have a soliton?
Yes, for example, let me explain, please, if you allow me. For example, any brain with cancer cell, and this model symbolizes spreading of cancer on the brain, for example. If gravitational potential absorbing belief, in this case, upper position of brain, the cancer cell will be speedily spread. If, for example, getting some pictures and Röntgen and the MR imaging, in this case, if cancer position is upper position of brain, in this case, we have this patient should be lie in a basic one, and this reduces to the spreading of cancer. If its location of cancer below on the brain, like this, it will be absorbed below. In this case, the spreading of cancer will be slowly. And we can infer from its situation, and by using parameter values of the solution what is the optimal and acceptable values of the parameters? What is this? We can find such a kind of results. This is also really important for biological models.
Thanks a lot, because it seems that it should be not only the importance of solitons is not only a mathematical, mathematical, but also as a submini. Okay, that is important. Exactly. Thanks a lot. It's very interesting. Thanks a lot. It's a pity that I lost the introduction. Thanks a lot, Professor. Thanks a lot.
Okay. Vabbè, altre domande da casa? Nessuno vuole intervenire? Qualche domanda al professore? Vabbè. Thank you so much, Prof.
Thank you. Thank you. It's a huge honor for me. Okay. I'm really happy to be here. And
I see you the next.
Sure. I will do my best.
Thank you. Ci sono foto?
Yes, we can. That's it. Thank you. Thank you.
Ringraziamo a tutti per partecipare.
Grazie della vostra presenza e della vostra pazienza.
Ci vediamo alla prossima discussione, forse ottobre, quando finirà la lezione.
Grazie.
Non è che sbagliamo le mascherine, no?